So the lab that we have today is one of the ones where it's really cool to see, to experience these personally, and it's possible to do at home. It doesn't require fancy equipment. But I also know that everybody's kind of in positions where, especially right at this moment, like, I don't know what is going on in your house or whatever. So whether it makes sense to actually do this stuff at this moment versus sometime in the next day or two. But what I want to do is introduce the lab, introduce the, kind of go over the basic procedures that are part of this, but then assuming that you're not like sheltering in place like on your own, like if you are, if you have nobody like in your pod or anything that you can actually get close to and touch, then there's some of these things you're not going to be able to do. But most of these, I mean, just from watching the little videos of you, I see people running around in the back and whatever. So if it's at all possible to do some of these at home, I would like you to do them at home and record what you find, and then on Tuesday, we're gonna be able to come back and share the experiences. But some of these, again, watching a video of it is so not the same. And again, these are easy enough to do that you can do them at home. So I'm gonna kind of do a little bit of background information on this lab. We'll talk about the different procedures, but then most of this lab is something that you're gonna do on your own. You're not gonna do kind of in real time Zoom together here, because you obviously can't reach out through Zoom and touch each other and stuff. So I'm gonna do some background information, like I said. Then I think what we are gonna do, we'll take another little break. I will talk a little more about the brain in terms of lecture material, just so we keep moving through stuff. So before 12:30, we're actually gonna cover a little more lecture material. But right now, what we're gonna do is talk about the general stimulation lab. So,
Dr. Egger, did you post the pages for the lab today on Canvas?
I just did.
Oh, okay, thanks.
Okay. All right, so we obviously haven't got into the peripheral nervous system in lecture yet, but this is going to be your introduction to it. The senses, I talked about, since there's both internal and external. In internal, you've got all sorts of receptors that are able to measure your body temperature or your blood pressure through the stretch of your blood vessels, or the amount of glucose in your bloodstream at the moment, or the angle of your joints or whatever. So you've got all sorts of internal senses, and we will be covering more of those as we go on. But the next three labs are all looking at these external senses. And the main ones, people don't really think about the five senses. People talk about touch and hearing and taste and vision and smell. These ones, these are what we call the special senses, and we're going to be looking at these later. The special senses are the ones that first, the receptors are localized in your head, right? Your ears and your tongue and your taste buds, your eyes, your nose, that's all in your head. And these all have more kind of complex receptors. You know, your eyeball, your ear, we're gonna spend like a lot of time going into the details of your eyes and your ears and things like that. Even taste buds are kind of complicated little things. The touch is part of what we call the general senses. So this is going to include touch, pressure, temperature, and pain. These are located all over the body. So as opposed to complicated receptors in the head for these special senses, when we look at, wait, Cassie, you have your hand up?
Oh, no, that was from before. Sorry.
So the general senses located all over the body, they tend to have very simple receptors. And we're going to look at them in more detail later. But sometimes they're just free dendritic endings even. There's not a lot to them. Even at their most complicated, they are little dendrites with a bit of connective tissue on them or something. So this is what we're looking at in our lab today. We're looking at these general senses located all over the body: touch, pressure, temperature, pain. So that's the first kind of background information. It's just kind of giving you a little bit of orientation of what particular branch of the sensory systems are we looking at. We're looking at these particular stuff right now. Later on, we'll look at hearing and taste and vision and smell, but next week. Some more terminology that we need. We need to talk about the idea of, you know, stimulus, which I mentioned, versus perception. We talked about that last time we did about the nerve stimulation lab, but I'll just kind of reiterate. Stimulus is an actual kind of physical thing happening in the world. Perception, this is your subjective experience of it. This is what you actually notice, what you're experiencing, right? If you had the voltage stimulator set for a really low current, there's still a stimulus. There's still some current going into your finger, but there's no perception. You didn't actually notice it if it was too low. It had to hit some threshold before you actually had a perception that there's something happening. But the stimulus is still there. Stimulus is just the thing that is happening. In order for you to have a perception at all, you know, the brain has to have information that something happened. And brain, which is basically trillions of neurons all interconnected. There's actually not the trillions, but billions at least of neurons all connected. And they all talk in electrical signals, right? We have action potentials and graded potentials and all that. So in order for your nervous system to actually know something is happening, you know, your brain doesn't know touch. Your brain doesn't know like light. All the brain knows is electrical signals. So for your brain, your central nervous system to have the information to process, the stimulus has to get converted into electrical signals, which then feed into the nervous system. And that process we call sensory transduction. So sensory transduction is important. You know, I'm sure there'll probably be a question on your exam, like, what is sensory transduction? The basic idea here is this is gonna be the job of some receptor, some little part of your nervous system that converts the stimulus, whatever it is, whether it's light or touch or, you know, some presence of sugar, and it converts that stimulus into some kind of electrical signal, which your nervous system can then process. So maybe I'll just type that out more formally using my little type tool here. So let me make it bigger because it's important. So So this is going to be an ongoing theme in our discussion of the nervous system for the next couple of weeks even. We'll look at how do the eyes convert light into electrical signals? How do the ears convert vibrations into electrical signals? How do your taste buds convert the presence of different kinds of molecules that you're chewing in your mouth into electrical signals? We'll be looking at that in more detail. But for right now, just kind of making sure you understand the basic idea that, unless you have some way to convert that stimulus into an electrical signal, there's no way you're going to have a perception because the nervous system doesn't have any information. That doesn't mean that there aren't all sorts of stimuli, like radio. I always use the example of like radio waves. Radio waves are all over the place going through the air right now. And if you have the proper thing to convert that, like a radio, you can actually realize, oh, there's like some signals coming into the room that are carrying information about music. And I can actually, if I have the proper equipment, I can notice that and interpret it. The same thing, like your touch receptors are detecting kind of deformations of your skin and converting it into electrical signals that your brain can then interpret as touch. Your thermoreceptors, the little things that process temperature, are detecting changes in temperature, but then creating an electrical signal, which goes to your brain and lets you know that there's temperature changes happening at your skin. One of the things that is kind of trippy about this, if you think about a person, and then the whole universe, everything else that's outside of you. The only place you have receptors are like on the surface of your body, right? You've got on your retina, you've got these receptors that convert light into electrical signals. Over your skin, you have these things that convert touch, physical deformation or temperature changes into electrical signals. In your nose and in your mouth, you have chemoreceptors, things that convert the presence of different molecules into signals. In your ears, you've got your eardrums that convert, vibrations hitting your body. And all of that kind of goes into electrical signals, go into your brain. And from there, you basically create a virtual reality of what must all this world out here be that would create that pattern of activity on the surface of my body. If you've ever seen The Matrix, if you haven't, you should see. It kind of brings up that same basic idea. It's like your sense of reality is basically taken in at the surface of your body through a bunch of receptors that are all doing the sensory transduction, converting those stimuli into some electrical signal going to your brain, and your brain does its best to create some model of what the world is that you can then look around and navigate through. But ultimately, it's always kind of weird. You kind of look out there and it's like, oh, there's a tree. It's actually, there's some light which is landing on your retina, which you are now using to build this model of what the world must look like that includes that tree out there. And again, that process is usually, pretty solid, but it's pretty easy, as we'll see later, to fool it and create all sorts of illusions. And also, when you have people who have different kinds of brain damage, you can have pretty major disturbances between how they are constructing their view of the world. But given that your brain is what's constructing your view of the world, you have this thing that gets really weird where people don't know something is wrong. Like from the outside, somebody who's looking at them or asking them questions, you realize that the way they're constructing reality is freaking bizarre compared to what you and most people would think. But from there, they can create an internally consistent kind of model of what the world is based on the way their brain is processing the information that they can't get out of. They don't know that it's not, that it doesn't, that it looks bizarre to you. Like for instance, people who lose parts of their brain due to strokes that process one side of the visual world don't know that it's weird that they only notice half of the visual world at the same time or at once, that they don't actually see the right and left visual field at the same time. And you'll ask them, like, imagine you're standing in your bedroom and looking out the window, what do you see? And they'll only mention the stuff like maybe that's on the left side of the world. And you're thinking, what about all this stuff on the right side? There's a bunch of stuff over there. And they're like, I don't know what you're talking about. And then if you have them turn around and imagine what it's like staring, like turn around 180 degrees and look at the room, they'll see everything that's on the other side of the room, but not the other side. So it gets really kind of freaky. This idea that there is often pretty severe distortions of what's happening in their processing, but they can't actually notice it. They can't get out of their own internal construct of what is real and not real. So that being said, make sure you memorize what is sensory transduction, because it's at the core of everything that we're going to talk about. This idea that in order to actually process things, you need to be able to have some signal that's feeding into your nervous system. The one other thing I'll put in here adaptation. So if you think about the world, there's so much stuff happening, so much information everywhere. And if you were constantly aware of everything all the time, you would just be, you'd be confused by, you'd be hard to know what's important, what's not important. What do I need to pay attention? What do I not need to pay attention to? So there is this thing that can happen. Sometimes it happens at the receptor level. Sometimes it happens more downstream, like centrally, like in the brain. But adaptation is this idea that you stop responding to constant stimuli. So when you put your clothes on this morning, you probably felt the material brushing against your skin, and then you kind of haven't been thinking about it. When you put your little headset on, you probably felt it clamp on your head, and then you kind of stopped thinking about it. When you put a hat on this morning, you probably felt, oh, feeling, or if you put yourself in a ponytail, you feel your hair getting pulled back, and then you stop thinking about it. Or you're wearing your glasses. You're not constantly thinking, oh, the glasses are sitting there on my nose and against my ear. So this idea that when a stimulus happens, you usually notice it. Usually kind of notice if there's a change. If you shift your glasses, it's like, oh yeah, I feel them. And then you let go of them, and then it's like a few moments later, it's gone again. This happens in all these different senses. It happens in hearing. Like, you probably notice, like, the heater's going when it turns on, but after a while, you don't even know it's going anymore. Temperature in the room. You walk into the room, it might be a little cooler or warmer, but after a little bit, you don't really notice the temperature anymore. Right? So all of your senses, there's a change, you notice something, and then assuming it's not something that is important that you need to deal with, typically the perception disappears. So the stimulus didn't go away, right? The temperature is still whatever it was. That heater or fan is still blowing, but you kind of stop noticing it's there. Some of the labs that we're doing today are looking at this adaptation, both like in touch as well as in temperature. Later, we'll see it in smell. When you walk into a new house or something, usually it's like, oh, this house has its particular smell. But after you've been hanging out for a while, you don't notice that smell anymore. Smell, just all of a sudden, there's no real smell. But when you first walked in, there was. The smell didn't go away. The smell is still there. It's just you've adapted to the smell. What is the one sense that does not tend to adapt?
That sight?
The vision does adapt. You
Vision.
don't notice it as much because you're constantly kind of shifting your gaze and constantly seeing something new. But if you kind of immobilize your eyes and don't let the visual scene change, everything starts turning gray. So even vision does this, although in a practical level, you don't notice it as much because your eyes are constantly twitching around and kind of refreshing and changing what they're seeing.
What about taste?
Taste also disappears. So
What about pain?
pain, so pain is usually the exception.
If it's a really, really small pain, then I think we can adapt to it, right? But
Let's talk about, pain. I mentioned pain as one of the general senses. The official word for pain is nociception. The nociceptors are the pain receptors. what, for most of these, we know what the stimulus is. We know, like for vision, the stimulus is light. For hearing, the stimulus is vibration against your eardrum. For touch, the stimulus is a physical stretching of your skin. What is the stimulus for pain?
It goes way up beyond the threshold.
So
Like it could be any thoughts like that happened in the past to you. Like if it's a painful memories, then that can be a pain.
that's different. You're thinking of like emotional pain. We use the words similar, and it can also, sometimes it can make you like have a physical feeling. But here we're talking about, what does it mean? Like, I have pain because like I just stuck a needle in your arm or something, or you just like walked into a door and broke your nose or whatever. What is
Like
actually,
damage of the tissues.
yeah. So typically this is like, like, you know, you know, impending or actual tissue damage. So there's something that is going to actually hurt your physical body. The nociceptors respond to different molecules that get released during tissue damage, for instance. Also, somebody mentioned it, pretty much any kind of receptor, if driven to the extremes of its range, can be perceived as pain. Sounds that are loud enough are no longer sounds. They're like they hurt. Because now you're in danger of damaging your ears and things like that. So pain is tissue damage. So this makes sense that you don't want it to really adapt. This is not something in general you're gonna like, okay, I noticed it, let's just like forget about it and move on with my life. If there's some like tissue damage, you typically are gonna wanna deal with it. Or leave it alone and let it heal or whatever, but you don't want to kind of pretend there's no pain. It becomes an
Professor?
issue. Yeah.
What's going on with something like CRPS, like complex regional pain syndrome, or when like there's a stimulus that's being detected, but it's actually there's not something physical there, but it's still being received as pain.
So that I don't know. I've never heard of CRPS. I can look that up and let you know.
Yeah, that'd be great. I'm interested. Thank you.
Okay. Okay, so pain is something that typically does not adapt. What else do I want to say about pain? Pain is also something that you have much more kind of fine sense of what's going on the surface of your body. The internal organs have pain receptors, but you don't have as much of a sense of the localization. It's like if you feel like pain on your neck or on your toe or something, you can usually say, oh, there's something hurting me on this part of my body or that part of my body. But if there is pain because you're having a heart attack and your heart tissue is dying, it's harder to know, like, oh, I feel, oh, my ventricle is hurting or something, so internal pain tends to be harder to localize, which is one of the reasons we're going to talk about referred pain in a little bit, part of our lab, because that is a diagnostic tool that you can use to help you understand when there's pain originating from the inside. There are other clues you can use that something's happening that actually are not about the localizing the pain from that particular organ. Pain management can also get really tricky, because if you do have like really bad pain, there are things that will turn off pain. Obviously, like morphine, or heroin, any of those opiates, oxycodone, hydrocodone, all fentanyl. What they do is will actually stop the pain messages from getting up to your brain. This is like good a time as any to kind of show how that works. So if I have like a pain receptor here, maybe it's in your finger or whatever, and it's going to go into your brain and spinal cord. It's your brain and spinal cord. And again, once it gets into your brain, you've got a sense of like, ouch, there's pain, right? So I have some signal here. There's some synapse, releases some neurotransmitter, continues up and goes to your brain. The synapses that are affected by your endogenous opioids are these synapses that are transmitting the pain signals up to your brain. But the receptors are actually not where you think they might be. The receptors for the endogenous opioids are actually on the presynaptic terminal. So let me kind of show this. It's pretty trippy. Oh, I want more of that. So if I look at this, let's look at this in more detail here. I have so normally this thing would release some neurotransmitter, which goes to here, and this continues to the brain. This is from the nociceptor. So the signal comes in, releases some neurotransmitter. These are the receptors for the endogenous opioids. And what they do is they inhibit the release of neurotransmitter from that axon terminal. So normally the pain message comes in, continues on towards the brain because we have this signal crossing the synapse. If you have the endogenous opioids like the enkephalins and things like that, they bind here. These guys here inhibit the release of the neurotransmitter. The presynaptic terminal. So this is even more of another version. We've talked about how our initial description of a synapse was kind of just a first approximation, that things get more and more complicated with presynaptic receptors and retrograde messengers and things like that. Here's another kind of complication. Like these opioid receptors are actually on the presynaptic terminal, and if they bind the opioids, again, which is coming in from some other neuron here, it'll actually stop the pain message from actually making it to the brain because it's inhibiting this terminal from releasing its neurotransmitter. So, does that make sense? I mean, obviously, another thing that the endogenous opioids do, they also work centrally. In addition to stopping the pain messages from getting to your brain, they also make you not care so much that you're in pain. again, was part of the reason they have really high addictive potential is because that part of it, you know, they just kind of make you not care so much that things are not okay. So they act both on the synaptic level here, where they just stop the message from getting to the brain, but then they also work by kind of just creating kind of a mental state where you don't mind as much what's going on. You're kind of dissociated more from the pain. So just kind of putting that out there. Again, we'll talk a bit about pain more as we continue on with our lab. Okay. I think we've covered everything. We've covered sensory transduction. We've covered adaptation. We've covered what are the general senses. We talking a bit more about what exactly is pain. So what we're going to do now is introduce the actual lab. And let's do that.
So are there any other senses that does not adapt besides the pain?
Yeah, some of the like proprioception, for instance, like knowing like the position of your body and things like that, where you kind of want to, you know, if you don't move, you don't want to all of a sudden just lose all sense of your body and all of a sudden feel like you're just a floating brain in space or something. So you want to kind of keep those messages coming that you have a body and what is your body doing. So some of those proprioceptors also don't adapt. So let's share screen. So let's see. So here we have the actual lab. You know, this picture here is kind of just giving you a sense of what are the receptors doing, what are they like in your skin, and it's worth kind of thinking a little bit about that to make the rest of this make sense. You know, here in your, this is supposed to be a little chunk of your skin, and this is just the outside of your skin here. And we have all these little receptors, you know, the Meissner's corpuscles. These are kind of like more light touch. Pacinian corpuscles is also more like pressure. These free nerve endings, like a lot of receptors, you can't even tell from looking at them anatomically. These might be temperature receptors or pain receptors, but you've got all these little, remember I said that the general senses have very simple receptors. These are all these receptors that are right under your skin that are giving you information about, you know, touch. And all touch is actually stretching of your skin, right? Or pressure, which is deeper, kind of pushing down in on your skin, deeper pressure. Again, or temperature or pain.
Quick question. You said those nerve endings are because they're part of the dendrite?
Yeah, so the basic idea is you've got some dendrites at the end of a neuron. Some of the receptors are what we just call free or naked dendritic endings, like temperature receptors, pain receptors. That's all they look like. They don't even look like something like special. They just look like a little spray of dendrites. Some of the other ones, a lot of the touch receptors have additional layers of connective tissue that are kind of around the dendritic endings, but it's still pretty darn simple. And we'll look at that in more detail when we talk about this formally in lecture. But so this picture is important to think about, like, you know, we're going to talk about 2-point discrimination. You know, this is another version of a threshold. This is basically saying, what is the closest we can have two little points pushing on our skin and still know that it's 2 points instead of one. So it's a threshold. It's just another version of a threshold. So here's your finger. You know, and I've got 2 points, two little needles coming down. If the needles are really close, you can't tell that it's 2 needles versus 1 needle. If the needles are further apart, it's like, oh, I know, I can tell that it's 2 needles instead of just 1 needle touching me. So I'm going to basically, this discrimination, 2-point discrimination is a threshold. What is the closest these can be and still notice that it's 2 and not just 1? Right? So it's a threshold. Maria?
So we will measure distance between the 2 points.
Exactly, the distance. What is going to determine that? What do you think is going to be important for determining whether or not, like, that minimum distance that you can actually feel as 2 instead of 1?
A different nerve ending,
And what about the different nerve endings?
like it's coming from different nerves instead of them like all coming from the same dendrites.
Right. So, and that's going to depend on what. So, what's going to influence whether or not it's coming from 1 or 2 or whatever?
How close the receptors are to each
How
other?
close the receptors are. So, you know, especially like in your fingertip, you've got receptors really close. The high density of receptors. These are supposed to be my little receptors here. Other places, like, you know, on your back, you have receptors, but they're not nearly as dense. So I could take these 2 needles here and I push them on my finger. I still know they're two separate, because this is lighting up here. Then I have another receptor that says there's nothing pushing here. And then this one is, you know, whereas on my back, if I push those same 2 needles down, it's like this dude's lighting up. This is not. For all my back knows, there is just one thing. There's no way for this situation here to know that there's 1 or 2, because I don't have this fine discrimination, because I don't have such a high density of receptors. What about if I put a needle here and a needle here? Could I tell that is 2 or 1?
In the back, 2, they're very separated.
Right, because now, even though these, you know, I don't have such a high density of receptors, there's still a few that there's one that's on, a couple that are off, and next one's on. My nervous system has enough information to say, oh, there's 1 here, and then there's a gap, and there's another one. So there's 2 rather than just 1. When we do this lab, normally we have this cool little thing where you can have these dividers that open and close. You know, for doing this at home, you know, you can, in fact, let me stop this. I can go back to, going in here. You know, I can just get a paper clip and I can kind of unfold it. You know, so you can do this really low tech. You need something where you can take two kind of sharp things And you want to be able to do it so you can adjust the distance and it'll hold that distance. I can make them like really close. And they'll kind of hold. I can make them really far and they'll hold. And the basic protocol is, for any kind of threshold, where do you want to start? If you're going to measure a threshold, what do you have to start with? I see Maria with your fingers like that.
Putting together, closer together.
Yeah,
No,
so
right.
if you want to find a threshold, you need to start at the point where they can't tell it's 2. So they need to be close enough that even though there are 2 little things here, that when they touch, and again, this can be, you have to do this on somebody else because your subject is not looking. And depending on, we're doing it on different body parts, either on their lips or on their finger or on the back of their neck or this or that. You have to start at a distance where they think, okay, that's 1. If they feel it's 2 already, then they're too wide. You're not going to find that minimum. But then you start spreading it and try it again. And again, you're not trying to fool them. You don't do something where it's like, boo, you feel that? Was that 1 or 2? You're really trying to get a sense of, can their nervous system, given a fair chance, tell that it's 1 or 2? So put them on, put some pressure. Don't poke holes in their face or something. It shouldn't be painful. It should be touch. It should be there with enough time that they have a chance to really make a fair choice. Is that 1 or 2? And then let go. And was that 1 or 2? And if they still said that's only 1, make them a little wider. It's like, oh my God, I feel that's definitely 2. And once you find when they really know it's 2 instead of 1, you're going to get a ruler and just measure what was that distance where they could finally feel it as 2 instead of as 1. Get close enough. I mean, I'm realizing, just demonstrating right now with this with this paper clip, it's kind of harder to make really fine adjustments. So, within plus or minus a millimeter, don't beat yourself up trying to bend it to 0.5 millimeter and get it to, but you should get within a millimeter or 2. What is the minimum distance where it really is 2 and not just 1? What's the source of variability here? That was one that we came up with also for the nerve stimulation lab.
If the participant can see it.
Say it again.
Mind wandering.
So there could be mind wandering. This one's a little harder because it's like, I'm touching you. You're paying attention to that.
Nerve damage.
That nerve damage could be something as well. It's another.
If the participant can see it.
Yeah, so they should have their eyes closed. You don't want them to see it for sure.
As we said in the last class, if the tissue has a lot of fat, if the patient is sweating.
So that won't make as much of a difference on this one.
No.
Because of, it's not about electrical stuff. So,
Okay.
hold on. What about, remember the whole thing about false positives? When you're working with the idea of thresholds, your nervous system is really ready to notice something sometimes, even if it's not there. This happens all the time in this lab. So how are you going to control for false positives?
You tell the subject, like, look, we're going to start the experiment right now. Relax, you will feel it soon. And you poke.
No, that was more
No?
about wandering and stuff.
Okay.
So let's say these were pretty darn close. In fact, this happens all the time. Somebody will say, like, I'll look at their data and they say they feel it on their face at like 3 millimeters. And I'm like, all right, let's go, let's check it out. Because nobody does that. So then you just go in like this, and it's like, no, definitely I felt 2. Right? So you want to double check. If your subject is saying they really feel 2, kind of go in and only use 1 on them and make sure that they feel 1 and that they don't still feel 2. I think some people, when we share our experiences on Tuesday, I am almost sure that some people are going to be able to have stories about their subject being convinced that there are 2 things and there's only actually 1 thing touching them. So I think that's one of the fun things about this lab. I mean, another thing is I think a lot of times people don't have a sense of how varied your sense of touch is across your body. People get this, they kind of fool themselves into thinking that they have a pretty complete experience of the world all around them. And this really shows that you are very limited by your sensory receptors and what kind you have and how they're distributed on your body. And it really limits how well you can detect the world around you. The next part, in fact, I'll show you that the other part, the touch localization, is very similar. I'm just going to show you a couple of little videos just to kind of show you what this looks like. So there is now this general sensation lab. It's got like the pages of the lab manual, and then there's doing the thing. I wrote here, do at home if at all possible. Right? I know that if you are sheltering in place all alone, you're not going to be able to do this 2-point discrimination. So in which case, you can just use the class data. But I really recommend you find somebody in your household to do this with, because it's cool and it's fun, and it really shows it in a way that I can tell you the results, but it's way freaking weirder to actually see the results in what really happens. So
2-point discrimination is the ability to differentiate one stimulus from 2. A lesion in the parietal cortex may impair normal 2-point discrimination. The fingertips can detect the presence of 2 stimuli when they are only 2 millimeters apart. The palms can detect 2 stimuli 8 to 12 millimeters apart. 2-point discrimination should be tested on both sides of the body for comparison. You may use 2 pins or 2 ends of a bent paper clip to test for this. Okay, Tom, if you could turn your hands over for me and close your eyes, and let me know if you feel 1 or 2 points.
Okay. 1, 2, 2, 1, 2, 2.
all right, so as you can see there, it's going to just be something like that, except here she was just double checking, is it in the right range? What you're going to do is something a little more involved, which is figuring out where exactly is the threshold. Where is that point where they only feel 1 versus where they can finally feel 2? And then record that number for that body part. The next is similar, but a little different. And this is called 2-point or touch localization. Somebody's going to touch you, your eyes are closed, and then you're going to try to recreate that exact same spot just based on feel. So here, this is a little picture what that looks like.
The materials you would need for this project is a ruler, 2 pens in different colors, and a blindfold.
Hey, is it okay if I blindfold you for this activity we're doing? It's called Tactile Localization.
That's fine.
Okay.
And you can just have your person shut their eyes. You don't have to blindfold them, although it could be fun.
gonna mark a point on your skin. And you're gonna have to mark where you think I marked.
All right. So before we continue here, just to make it clear, la, 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 la. You're going to need two different colored pens, right? Because you're marking on them and then they're marking, and you want to be able to measure the difference between where they marked versus where you marked them. So you need two different colored pens. And the other thing, it's not so clear from watching her in the video, but you really want to mark and this is not about fooling somebody or trick, right? You're gonna put a mark and really be clear, like rest the pen there, really make sure it's like they feel that's the point. And then your subject, either blindfolded with the eyes closed, they're gonna feel around. And again, they're not looking. And again, it's not like they really want it. It's like there, it's really, I think it's right there. And then they're gonna mark exactly where they think they felt it. And I think you are going to be weirded out at how bad we are at this. Like you're sure you're touching the exact spot that the person put the pen down. And it's, yeah, that's part of the reason why I want you to do this for real, is because I remember the first time I did this, the first time I did this, I was like, what? I just kind of assumed that I would get it perfect. And, you know, obviously the more sensory receptors there are, the better you're going to be at it. And you get further away from where have a nice dense like receptor array. I think you're going to be like, it's cool. I find this lab really, really like kind of giving you a real sense of, oh yeah, our ability to sense the world really is limited by our senses, by our receptors. So let's get back, follow.
Okay. All right. Okay. All right. So now I'm going to get your pins up, and I'm going to measure the distance from the actual point where I marked and the guess point where you marked.
Obviously, you're going to be writing this in your lab notebooks as you get this data. Yeah.
All right. Thank you so much for your cooperation. I appreciate it so much that you volunteered. You're so very welcome.
All right. And yeah, you can thank your subject when you're done. Anyway, so you're going to do this at home, record your data. And again, we also have class data that you can use, but I really do want you to do this on your own, if at all possible, because it's the way you're really gonna truly understand what's going on here. The next part, adaptation of touch receptors. Just follow the protocol in the book, in the lab book. It's basically you're going to be putting some coins on your arm. This is also, you're going to need a second person. Somebody's going to put coins on your arm and you're going to feel them, and then you start a timer. Everybody at this point in the, in the world has an iPhone. So you just start the timer on your iPhone and you wait until they don't feel it anymore. And it happens pretty quick. And it should be about touch. If you're using coins where the temperature becomes an issue, that's not so good. And that's why we often put a piece of tape on the coin or something so they're insulated. But usually within 15 or 20 seconds, you're going to probably find, like, if I'm really being honest, I have no idea that I feel anything on my arm anymore. So do that one as well. Once you have all of that data, you'll be able to discuss what you find there, as well as, again, I have this spreadsheet here that has data from previous classes, but I don't want to actually go into the results until after people have actually done it and you have your initial experience. So on Tuesday, we'll review the kind of the class data for this. Adaptation of temperature receptors. So this one is also something you can do at home. You just need a bowl and you need, water at different temperatures. The temperature, in the lab manual, I actually talk about specific temperatures to shoot for, because I want this to be about temperature adaptation and not about pain. But since you're doing this at home, so when you're doing the temperature adaptation part, there's two parts. One of them is you're going to have a thing of, hot water, but it's not painful. So whenever we say hot, this is not painful. It should just feel nice, kind of like bath, like a nice warm bath. When we have cold, it's also not painful, kind of cool and refreshing, right? A lot of times people go overboard and, like, they're writing in their lab book, what is the experience of having your hand in this? And it's like, it hurts. It's like, no, then it's too hot or too cold. It shouldn't hurt. It should be cold or warm or not much temperature experience at all. So I just want to say, not pain in any of these. If you are experiencing pain, back up, change the water so you're not in pain. And also your observations are about temperature. Like when you're describing your experience, yes, it's wet or whatever, or, but I want you to actually tell me, does this hand feel warmer or cooler than the other hand? Like, give me your experience, your subjective experience of temperature, of warm and cool. Also, if you've ever been in a hot tub, you probably know that once you're there and you don't move, all of a sudden it feels a little cooler. And then as soon as you move, it's like, whoa, it got hot again. It's like the temperature didn't change. You got this kind of layer that ends up right against your skin that kind of insulates you. So if you really want to know the temperature, you got to wiggle your fingers around. So observations are around the temperature. I'm going to say wiggle your fingers. Wiggle your fingers and decide, what does the temperature feel like? And there's going to be two different things we're going to do. One is there's just going to be a thing with like kind of hot water. And you're going to put your hand in, and start a timer. And what does it feel like? You just follow the thing. And then you're going to put your other hand in after like, I think a minute or two. And then you're going to, again, compare. What is wiggle your fingers around. What does the temperature feel like on this hand that's already been in the water for a while versus the hand that just came in, right? So you are describing your experience of temperature in the different hands, comparing them, making sure you wiggle your fingers around so you can really feel the temperature. This is where it might be useful having somebody else actually recording your observations, because your hands are wet. You're going to mess up your lab book if you're trying to write. You can't write if both hands are in the water and you're doing this. So this is where you can either get one of your potting pals to actually record your data, or else you can have them do the experiment and record their experience. Either way. The other one is you're going to have 3 bowls. And cool room temp, warm. So before you actually start the experiment, use your finger, check. Okay, I can really tell there are 3 temperatures. This one is in the middle of these 2. Make sure they're not painful. I put a little link showing somebody doing something similar to this, but they're using ice. Don't use ice. Ice is pain. So I wasn't even sure I should put that video on there, but I put it on there because it kind of shows the basics thing so you can see kind of what it looks like. And then you're going to put one hand in the cool water, one hand in the warm water. And again, discuss, what does this one feel like? What does this one feel like in terms of temperature when they first enter after 2 minutes? Again, follow the protocol, read. This is where you really need to make sure you read the protocol. And then after 2 minutes, both hands go into this middle one. Again, wiggle your fingers around. And again, make sure you think about the temperature. Like, what does the temperature feel like in this hand? What does the temperature feel like in this hand? If you've never done this, it is freaking weird. It's both hands are in the exact same water in an exact same temperature, and you are probably going to find your experience is very different for the different hands, because whenever you are in a particular temperature, your hands adapt. And the temperature starts to not feel like much of a temperature at all. And then when you change, you can kind of imagine what's going to happen. This one, is kind of adjusted to this is normal, and now all of a sudden it's getting warmer. This one is adjusted, oh, this is normal, and all of a sudden it's getting cooler. I think if you've never, this is something, I did this, I remember when I was a kid, and it was one of the things that totally kind of blew my mind and got me like kind of lifelong interested in kind of senses and sensory processing and stuff. I highly recommend you do this and record your data, in your lab notebook, and not just, again, it's wet or it's like, oh yeah, it's kind of weird. Specifically think about, what does my right hand feel like in terms of temperature compared to my left hand temperature right now as you're doing this. So blah, 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 blah. Just kind of encouraging you This you can even if you are just alone at home with your cats, you can still do this one. You don't even need anybody else. You can just do this one. So any questions about that? The last part, part 5, I don't really, you can do at home if you want. I'm going to explain it because it's important to understand, just because it's an important clinical concept, this idea of referred pain. Typically we do typically we do have a subject in the class or in each group demonstrate referred pain, but we don't have everybody do it. And I know it's uncomfortable. Usually there's somebody who's like up for it. But I don't want to just say everybody should put themselves through kind of gratuitous pain right now. So if you want to follow this protocol, it involves sticking your elbow in ice water. Feel free to do it and record your data, or else you can, just in your lab notebook, you should at least talk about what people tend to find and why it's important. But I am not asking you to actually do this if you don't want to, because it's really uncomfortable. So let's talk about referred pain. This is the last piece. So the basic idea here is when you have pain that's originating in deeper organs, it's often hard to localize or try to really know definitively what is actually hurting inside of me. And there is this concept of referred pain where even if there's pain from deeper organs, it often manifests as feeling pain on different parts of your body that aren't actually in pain. So the idea here is, let me draw a person. Here's their heart. And I'm actually not exactly sure exactly how all these neurons are connected up here, so I'm just gonna play a little fast and loose with my drawing, but it's gonna be close enough. So you have basically neurons that are gonna be coming from your heart and ultimately tell your brain like there's something wrong. There are also going to be neurons coming from your arm that also are coming up and telling your brain like my arm is in pain. And what happens is you get this kind of crosstalk where you might have pain from your heart, you're having a heart attack. And there's all these messages coming saying that the heart tissue is in trouble. But then there's this crosstalk happening. So all of a sudden it excites, and now there's messages that are coming also that the brain is interpreting as having started in your arm, but actually they didn't start in your arm at all. It was this kind of crosstalk that happened along the way. So in your brain, it's like my arm, like you're feeling pain over here in your left arm, even though the left arm has nothing causing it pain. Instead, it's actually the heart attack that's causing the pain. But this crosstalk is causing what we call referred pain, is when the pain gets referred someplace else other than the origin of the pain. We'd say that pain from the heart is being referred to the left arm here. So that's this basic idea of referred pain. Like it feels like the arm is in pain, but actually it's the heart that's in pain. And there's lots of different examples of this. Your, you know, in fact, if I, here, I will, I want to get into Firefox because Firefox is better. Okay, I'm going to go to images, referred pain, and I'm going to share. You know, these basic pictures like this. Oh, that's too small. Let's get a bigger one. Right, this is kind of showing where on the body do you often experience pain, even though that the pain is ultimately originating from a deeper organ. So that's what this idea of referred pain is. It's like this person is feeling pain on their arm or on their back, or their shoulders or their butt or something, or their thighs, but it's not actually originating from there. It's actually this referred pain. It's this crosstalk that is being caused by deeper pain from an organ.
Is crosstalk between neurons?
Yeah, yeah. So the lab has a procedure that you can do if you want. Again, not necessary. So I'm going to say optional to do. You should write about referred pain in your, minimally I want to see in your lab notebook that you tell me what it is and why it's important. Because I want you to leave the lab understanding that. But in terms of demonstrating it, the way we demonstrate it is this. In the lab, we have ice water. From your chemistry, what is the temperature of ice water?
$32 Fahrenheit.
So 32, or since we were in the metric system, what would it be?
0 degrees
1,
Celsius.
2 degrees.
Be
Zero.
So 0 is the only temperature where both ice and water can coexist. So if you have ice and water in equilibrium, you know that it's 0 degrees. Ice can be colder than that. Ice can get super duper cold. But if you have ice and water in equilibrium, it has to be 0 degrees. In fact, this is how you calibrate temperature probes and stuff. And 0 degrees is cold enough to cause pain, but it won't damage your tissue permanently. You're not going to get frostbite from being in ice water bath that's in equilibrium. You can get frostbite from touching ice that's super cold. But if it's in equilibrium, so when you're doing this, if you do this experiment at home, make sure the ice and the water are in equilibrium. They're both, they both have had a chance to become the same temperature. So then we know we're at 0 degrees and you're not going to cause tissue damage. It's just going to hurt. We're going to use this as well when we do the blood pressure lab, the cold pressor test. Is you stick your hand in ice water. It's a classic way in research to cause pain without causing lasting tissue damage, is to have somebody stick their body in ice water. What we do for this lab, and again, you can do if you want, but you don't have to, is you take your hand, and you put your elbow in the ice water. I want to, who needs to get muted here? Somebody is really loud. Make sure you mute yourself when you, there we go. So you have your hand in ice water. Things to notice here. Here's like the pinky. If you remember from your anatomy, there's the ulnar nerve, which is taking things down from this side of your hand. The ulnar nerve is kind of going through here. What you find, and notice the hand is just in the room. The hand is not experiencing any kind of stimulation. The hand is happy. You know, the hand is just, but the elbow is not happy. The elbow is in pain. And if you describe what you feel, I'll just kind of talk about, I'll mention what happens. And then if you want to do this, you can do this, although again, it's not that comfortable. At first, your hand feels fine. And when you stick your elbow in here, it's like, whoa, that's really cold. That kind of hurts. And then you wait 1 minute, 2 minutes, 3 minutes. You start feeling this weird cold sensation start moving up your arm. Even though your arm is not experiencing cold, eventually your hand starts feeling cold. Eventually your hand starts actually feeling like this weird dull pain that's like really uncomfortable, like cramping and weird. And there's nothing going on. Your hand is just hanging out in the air. But you've got all this activity of pain receptors down here, which is going up the same nerve, which is carrying the messages for the receptors coming from here. And you start getting that weird crosstalk going on. And your brain starts thinking that, oh, my hand is cold and in pain, even though it's actually your elbow. So, you know, that's just, if you want to prove to yourself that you can feel weird stuff on your hand, even though your hand is not actually the part that's getting the painful stimulus, you know, do this at home. Minimally, you should, again, write up the basic idea of what happens with all this. So are there any questions about that? So again, the idea of referred pain. Right. I mean, most people probably have heard like a symptom of a heart attack is pain in your left arm, you know, and you're wondering like, why does that make sense? You know, it makes sense because of this kind of phenomenon. So there is a part 6 that we're not doing. The lab that has part 6, like, what does it say? Relative density, relative density and location of touch and temperature, don't do that. We are not doing that. But sometime, today is Thursday, sometime in this Friday, Saturday, Sunday, Monday, sometime in the next 4 days, you should, again, assuming that it's not just you and your cat, and if it is, then, you know, just get the data from, you know, I don't go out and risk catching COVID just to get your lab data. You know, one, again, there's going to be the 2-point discrimination. You know, do that. 2, the touch localization. Do that. 3, there's the touch adaptation. You know, do that. Each, you know, and this won't take you that long. And I think you're going to find it's really kind of fun and kind of weird and cool. The next one was the stuff with the temperature adaptation in the water. You know, this one you should be able to do even if you are just on your own, because it's just you and some bowls of water. Although it's better to have somebody to record the data, because you're going to have both hands in water. So it's always better to record what people are experiencing as they experience it, rather than kind of try to remember and write down what I remember it was. There's more of a chance that there's some mistake or something if you don't record things as they're happening. And then 5, you know, the referred pain. Like I said, this you can do if you want, but minimally discuss the concept. So just kind of putting it out there. I am not, you know, you're not going to get docked for not putting yourself into a painful, there's probably enough stuff stressing you out right now that you probably don't need to add additional pain into your life here. So any comments, questions about expectations for this lab? You know, I think you'll enjoy it. I think you will have fun with it. I know this part is something that people did in Bio 110, although we're doing it a little more formally, and we're going to kind of bring our data together and discuss more about what it means. And then tying it in with touch localization, I think is really kind of cool, because you see these 2 different things that will fall out from the relative densities of touch receptors in different parts of your body in very observable ways. And then, like I said, part 6, don't do. So just kind of reminding you, in case you're like thinking about that, you don't got to do it.